So hi guys, my name is Calvin and I'm currently the leader of our lab subgroup on computational historical linguistics. And today I'll be presenting on neural protoform reconstruction of Middle Chinese. So first things first, I should let you know that, this meeting is being recorded. So, all right. And first, before I begin, I'd also like to thank my advisor, David Mortensen, because he basically mentored me as I started my NLP journey and my MLT. So I went from like an average CS student who hadn't even taken 10601 machine learning to be able to publish in NLP conferences. So this could be you too, by the way. And I also like to thank my lab mates for making research super fun. So I haven't had this much fun in like a long time. Great. All right. So the talk will start with a brief introduction to what historical linguistics is. Then I'll move into the data set we've constructed for computational protoform reconstruction. Then I'll talk about our paper that was recently accepted to ACL 2023, just yesterday. And then we'll talk about some other research efforts, such as our ongoing VAE research and our phylogenetic inference that we've submitted to Sigmorphon. And finally, I'll conclude with our goal for EMNLP 2023. So let's talk about historical linguistics in a nutshell. Historical linguistics seeks to answer the question, what did older languages sound like? So we call these older languages proto-languages, and these are the ancestor languages from which modern daughter languages descended. So what started as dialects of a proto-language accumulates sound changes over time until the dialects become mutually unintelligible and they become separate daughter languages. And of course, proto-languages are no longer spoken today, but we can infer what they sounded like using comparative method. So according to the tree model of language change, the dialects of the proto-language branch off and become independent languages. So we say that all these, the modern day languages, the daughter languages, are genetically related through their ancestor, the proto-language. Now, on each edge of the tree, we have a series of sound changes. Now, of course, this model ignores dialect borrowing, but it's still nonetheless a useful heuristic for understanding how languages are related to each other. Now, we can keep going up the tree. So Romance is a proto-Romance is actually a subtree of the greater Proto-Indo-European tree. Right. So let's talk about what protoform reconstruction is. So this is the inference of morphemes or words as they appeared in the proto-language. Historical linguists use the comparative method to perform this task, which involves finding patterns of sound change in the daughter languages. Now, this relies primarily on the neo-grammarian hypothesis, which assumes that sound change is regular and applies to all words that meet some conditioning environment. In other words, sound laws suffer no exceptions. So I like the analogy that my advisor uses. So imagine you had a regex and you applied it to most of the words in some proto-language. And that regex is sound change. Now, protoform reconstruction then is trying to undo that regex and figure out what the original proto-language is. So it's kind of like a decoding problem. Right? So the first step of the comparative method as linguists perform it is to group words that descended from the same proto-word to form cognate sets. Now, the same language family can, this is important because the same language family can have multiple ways to express the same concept. So for example, I'll draw from Mandarin and other Chinese languages. There are many ways of expressing the concept tiers in a Chinese language family. And there are different characters. So for this language family, at some point along the tree, a language made some lexical innovation and created a new word based on a proto-word. Right. Now, in the case of Romance, we can, after we identify these cognate sets, we come up with rows of cognates that appear similar in pronunciation and share the same meaning. So here's an example of a cognate set from Romance. Okay. So the second step of the comparative method, after we do cognate grouping, is to find the sound correspondences among the reflexes or the daughter phones. Right. A reflex is just a sound in the daughter language. Right. Then, after we identify sound correspondences, we reconstruct the proto-sound. So we use a few heuristics for reconstructing a proto-sound. For example, we can use directionality, which basically says sound change in one direction is more likely than the other. We can also use a phonological motivation, such as assimilation, to try to infer what the proto-sound was. We can also use majority wins heuristic, and among others. Right. So now let's frame protoform reconstruction as an NLP task. So we can treat it as a mapping from cognate sets to protoforms. So cognates, again, are words deemed to descend from the same ancestral form. This requires cognacy annotations by a linguist, or we could perform automatic cognate detection, as has been done many times in the literature. So here's an example of a cognate set from the Chinese language family. We say that all these words across these daughter languages are related to each other through their common character, which means doggo. Right. Now, the protoform, the output of our NLP task, is the ancestral form of the morphemes or words as they appeared in the proto-language. And in our case, the proto-language is Middle Chinese, and the protoform is Kun. Now, of course, I can't tell you what the tone is because we don't know the actual phonetic value of the tone from Middle Chinese. But we do know that it was tone 2 out of the 4 possible tones in Middle Chinese. Right. Now let's move on to our efforts to build a data set for computational reconstruction called WikiHan, which was published at Coling 2022. So just as a primer on the Chinese languages, this is a language family that consists of many mutually unintelligible varieties, which linguists can cluster into 7 well-defined subgroups, the ones listed here, as well as a few other disputed ones, like Jin, Hui, and Pinghua. So the Chinese languages revolve around Mandarin, which is the language of administration in Chinese-speaking societies today. But other non-Mandarin varieties are also spoken as well, but they're not written, which is very important. However, recently, it's been possible to transcribe these non-Mandarin varieties through Chinese characters or through romanization. So here is an example of different ways to romanize the transcription of doggo in different Chinese varieties using each language's specific romanization. So the most famous one that you might know of is Mandarin Pinyin. So Middle Chinese then basically is the proto-language of most of the Chinese daughter languages today, except for the Min languages, which descended from Old Chinese. Now, how do we know what Middle Chinese sounded like? Well, luckily, in the case of this language family, which is quite rare, we actually have a document called the Qieyun, a rhyme dictionary compiled in 600 CE, which groups the pronunciations of different Chinese characters into equivalence classes. Now, of course, we don't know what the actual values of the equivalence classes are because the IPA did not exist back in 600 CE, but it still gives us a head start as to what words can be grouped with each other and what words rhymed with each other. So our goal then in creating this data set is to enable comparative reconstructions of Middle Chinese using the modern Chinese languages. Now, why do we want a computational reconstruction? Well, this is because it's very painstakingly laborious for a linguist to perform the comparative method and try to remember all the possible cognates in the language. Whereas with a computer, it's pretty simple to process many cognates at once. Another issue is that different linguists will often arrive at different reconstructions. So that if we use a computational model, then our reconstruction becomes reproducible by anyone who wants to run our code. And finally, our goal is not to replace the linguist, but rather to provide data-driven suggestions for a historical linguist as they're performing a reconstruction. Okay. So we contribute a dataset WikiHan, which consists of 67,000 pronunciation entries across 8 modern Chinese varieties, as well as Middle Chinese. We scrape the data from Wiktionary and convert it into IPA. Finally, we validate our data set on the protoform reconstruction task. Right. The first step of our data set construction involved converting romanization into IPA, And this is important because during protoform reconstruction, we don't want to compare graphemes or romanizations. Rather, we want to compare phonemes during reconstruction. So we used a G2P model written by my professor and to convert into IPA. Then we obtained Middle Chinese entries from the Qieyun using a transcription from Baxter and Sagart, who are leading stenologists in the field, using Python. And we convert Baxter and Sagart's transcriptions into IPA using Epitran. So some important note is that our dataset is restricted to single characters, which if you know the Chinese language family, a lot of times it's difficult to compare words across different varieties because different varieties will use different characters to represent the same concept. All right. We want to avoid issues of partial cognacy, for example. Also, so then we choose the dialect with the most data on Wiktionary to represent that entire subgroup. And here are the final statistics of the different varieties represented in our data set. Now, we made sure that we included one variety from every major subgroup. But of course, our data set unfortunately favors higher resource varieties like Mandarin, Yue, Wu, and Min. Now, our dataset isn't just useful for comparative reconstruction, though. It can also be used for dialectometry, which involves quantifying relationships between linguistic varieties. We'd also perform improved phylogenetic inference of Chinese. And finally, our model could also be useful for speech applications for lower resource varieties of Chinese beyond Mandarin. All right, now let's talk about the work that was recently accepted by ACL 2023. So first, we need to talk about computational protoform reconstruction methods in the literature. The previous state of the art before our paper was Maloney et al. 2021, which built a character-based sequence-to-sequence model using an encoder-decoder-based RNN with attention. Well, actually, it was a GRU, but it's within the RNN family of architectures. Now, they performed Latin protoform reconstruction using 5 daughter languages from the Romance language family. We simply re-implemented their Dianet model in PyTorch. And if you'll notice, now, how do we feed in a cognate set? So simply, we take all the cognates all the entries within a cognate set and concatenate them together. And we also add a language embedding and a phone embedding for each phone. Now, this might run into limitations with longer language families, such as Austronesian or Oceanic, which has 600 daughter languages. So because RNNs cannot handle super long sequences. But it works for our case because the Latin data set only has 5 daughters in that data set. Yeah. Now we can evaluate the protoform reconstruction task on a few criteria. So the first is accuracy. So what is the percent of reference protoforms that the model reconstructs exactly, phoneme by phoneme? Now that's a pretty strict metric. So then we can also evaluate by phoneme error rate, which compares the edits between the hypothesis and the reference protoform, calculated in terms of phonemes instead of characters. This is important because this accounts for the fact that many phonemes often require more than one character to encode in Unicode. And we can also calculate feature error rate, which calculates edits in terms of articulatory phonetic features from panphone. So this assigns partial credit to phonetically similar hypothesized phones. For example, if we predict P for B, then we want to give partial credit as opposed to predicting X for B, because X and B are not as phonetically similar as P and B, which only differ in voicing. Right. So we compare Maloney et al.'s architecture to a few baselines. So the first is the random daughter baseline, which randomly designates a daughter as the protoform, which basically assumes that no sound change occurred. So for example, we can randomly say, okay, let's roll a die. It's Shanghai's lucky day. Shanghai is like some Shanghainese Wu is the protoform. Right. We also compare to the majority constituent baseline, which is more driven by historical linguistics. So there's a heuristic called the majority wins heuristic, which says that within a sound correspondence, we go with the phoneme that shows up the most in the daughters and take that as the proto sound. Now, obviously, this is not necessarily accurate, but it's nonetheless used sometimes as a heuristic. And simply what we do is we syllabify our daughter data into onset, nucleus, and coda, syllable constituents, and we take the most common phoneme sequence within each onset, within the nucleus and the coda. Right. Now, our results show that Maloney et al. 2021 outperforms both baselines on all four metrics on our Wikihan dataset, which shows that our dataset is useful for computational protoform reconstruction. Right. Now let's talk about our contribution that we submitted to ACL. So we simply replaced the seek-to-seek architecture of Maloney et al. 2021 with the state-of-the-art transformer architecture, which is the state-of-the-art for neural machine translation. Okay. So we evaluate our model on 3 data sets. So we have a romance data set from Maloney et al. 2021, which comes in 2 flavors. One is in IPA, and one is the orthographic forms. We also contribute a new data set from Ho 2004, which contains 39 varieties across 800 cognate sets. So this is slightly different from Wikihan, which has 8 daughter varieties, but 5,000 cognate sets. Right. So our results show that the transformer outperforms the RNN and the baselines on all metrics. See the bolded results. So we basically set a new state-of-the-art for Latin protoform reconstruction. Now, this is fairly surprising because if we go back to the previous slide, we see that the data that the model is trained on is fairly small. So this is essentially a low resource setting, but the transformer still outperforms the RNN baseline from Maloney et al., as well as the other baselines, like the majority constituent and the random daughter. So we then try to understand what our model is learning. And we basically create a distance matrix by taking each language embedding learned by the transformer and computing cosine similarity between every pair of languages. So this shows like to what extent is language 1 related to language 3, for example. And on this distance matrix, we perform hierarchical clustering using Ward's minimization algorithm with sklearn. And we see that the RNN model from Maloney et al. 2021 fails to learn a phylogeny. So we compare the gold phylogeny of the 5 languages involved in the data set, and we compare to the RNN one. This tree is quite frankly not accurate. But we see that our tree right here is accurate. You might be confused by the switching of Portuguese and Spanish, but that actually doesn't affect like the accuracy of the phylogeny.
You can just say it's a topology that matters of the tree.
Yeah.
It's not over. Yeah.
Okay. Yeah, the typology of the tree is accurate.
Because so that's some compliments.
Yeah.
Yeah.
But we want to caution that our phylogenetic analysis is primarily distance-based, which calculates similarity based on phonological similarity among the daughters, which is not actually the preferred method of phylogenetic inference for linguists, which we'll talk about later. Okay, so now I'll talk briefly about work done by other graduated members of our lab who worked on a variational autoencoder architecture for their MIIS capstone. So the whole motivation behind using a VAE is that given proposed protoforms, we should be able to derive the daughters from the protoform. So when a linguist proposes a set of reconstructions or protoforms, we should be able to trace using rules to go from the proposed protoforms to reconstruct the daughters. That should be predictable. However, previously, our transformer and RNN models only model the opposite direction, going from the daughter phones to the protoforms. Now, this is very difficult because there are mergers that you cannot undo with a transformer or RNN model. Whereas in the other direction, if you're modeling historical sound change from protoform to daughter, then you could simulate the mergers as they happen for us in time. You don't have to undo the merger, which is the harder problem. So what we do is we simply add a protoform to daughter decoder that takes in the protoforms and tries to predict the daughter forms. right? And our architecture basically becomes daughter to proto to daughter, which basically looks like an autoencoder architecture. Now, instead of using vanilla autoencoders, though, we use variational autoencoders, which learns a more expressive latent space. Right. So here's the diagram of the architecture. So simply, all we do is on the latent space learned by the transformer encoder, we can take the latent space and add a transformer decoder to sorry. So what we had before was to take the latent space of the transformer encoder and to predict the protoforms. But now we're adding this top part, which basically takes the same latent space of the encoder and tries to predict the daughter forms. So this is sort of a regularizer on a model to ensure that the protoforms learned don't become too crazy and we're still able to reconstruct the daughters from our reconstructed protoform. Right. So our results show that the VAE transformer outperforms the transformer after taking the average of 3 runs on the test set. Right. Okay. Now, currently, we have one member of our lab working on a VAE architecture. And instead of trying to take the output of the transformer encoder and predict the daughter from that, or predict the protoform from that, instead, what we're going to do is to pass the hidden state of the decoder, of the protoform decoder, into a second set of encoder decoders, which is designed to predict the daughter. Now, the challenge, or the reason why we have to pass the hidden state of the protoform decoder into our second set of models is because argmax is not differentiable. So you cannot pass the predicted protoform to this transformer encoder decoder. We want the whole architecture to be back propagatable. Okay, now let's talk about our work that we submitted to Sigmorphan last week. So phylogenetic inference is the related problem in historical linguistics that seeks to answer how did the proto-language split off into its daughters? So this is the process of determining how the daughter languages branched off from other languages in the same language family. So it takes as input the protoforms and the cognate sets and outputs the language family tree. Right. Now, this is usually done with Bayesian inference, which tries to find the posterior probability of some tree given the daughter data. So going back to the tree model, recall that the root is the proto-language, and the internal nodes of the tree are intermediate proto-languages of the proposed subgroups. So for example, in this case, proto-romance, sorry, it's a little blurry. Proto-romance is the proto-language, whereas we can also identify intermediate proto-languages, such as Northern Romance, Gallo-Romance, Ibero-Romance, etc. Now, obviously, we don't have data for a lot of the intermediate proto-languages a lot of the time. Right. Now, when a linguist performs phylogenetic inference, the only acceptable way to do it is to use what we call shared innovations, which basically means sound changes shared by 2 or more daughters. So if 2 or more daughters share some common sound change, which can be likened to a mutation in DNA, then they're likely to be related. Right. So here's an example of a shared innovation. So we compare the Latin protoform anima to the Spanish daughter form alma. We can infer that N changes to L and I gets deleted. Now, of course, the shared innovation method depicted here is misting the environment, which is very important when linguists actually infer shared innovations. Okay. So our contribution in our Sigmorphan submission then is to replace the expert at different stages of phylogenetic inference. So our goal is to learn intermediate sound changes using a phonological prior that weights possible sound changes by feature edit distance using panphone, as well as a typological prior that uses a neural network trait that learns the probability of some articulatory feature changing from the different sound changes. And finally, we contribute a sound law induction method using a minimal generalization learner from synchronic linguistics. So the methodology of our phylogenetic inference package starts with alignment, or actually, let's start with the input. So we take in as input a Tucanoan daughter data and proto-Tucanoan protoforms from Chacon 2014. Tucanoan is a language family in South America, and we are fortunate to have daughter data, cognacy annotations, protoforms, sound laws and intermediate sound changes from an expert, namely Chang 2014. Now, our goal is to see how well a computational model can replicate the intermediate sound changes and sound laws that Chang 2014 identifies. The first step in phylogenetic inference is to perform alignment of the protoforms and daughters. After that, we induce sound laws from the aligned forms. Then we encode shared innovations into a transition matrix, which is then fed into phylogenetic inference. And finally, we get out a Tucanoan phylogeny that we can evaluate against a gold tree using a metric called generalized quartet distance. And I'll go into each of these steps in detail here. So the first step is to align the protoforms and the daughters using Needleman-Bunch alignment, which is just a variant of Levenshtein edit distance, but we revise it to output the insertions and deletions. All right, and then next, we want to align the protoform right here with the daughter form. And then after that, we can apply Wilson and Lee's minimal generalization learner to learn sound laws based on these the aligned protoform and daughter forms. Right. Now, the next step is to encode the shared innovations into a transition matrix. So if we look back here, these are the shared innovations learned by the minimum generalization learner. Right. And we want to encode these innovations into a transition matrix. So basically, one important part of Chang and List's methodology is to realize that sound changes don't happen overnight. Like they don't jump from the protoform to the daughter. Instead, they go through a series of intermediate sound changes gradually over time. And so to help us identify these intermediate sound changes, which often go through phonetically similar phones, we put every phone in the universe into a small graph, well, actually a 550 subset. And we create a fully connected graph of phones where the edge between all possible pairs of phones is weighted by the feature edit distance between the two phones, which reflects the phonetic similarity between the two phones. Then the intermediate sound changes then that we identify are those on the shortest path from the protoform to the reflex. So, for example, here are the intermediate sound changes that Chang and List identify in their 2016 paper. So if the proto sound is K and the daughter reflex is H, then the expert posits that there are two ways that K can turn into H. K can turn into G can turn into H, which can turn into H, or G can turn into Ch, which can then turn into Sh, and then turns into S, and which turns into H. Okay. Now we want to do this with our phone graph instead using computational methods, because a lot of times it's very we can't just wait for an expert who has experience with some language boundary to come up with all the intermediate sound changes and the shared innovations. Right. Now we take our phone graph one step further and learn what's called a directional weighted feature edit distance using a neural network. So basically, we feed in the proto sound, we extract a panphone vector using articulatory features, we one-hot encode it, and we feed that into a neural network, which learns to predict the probability of each feature, articulatory feature changing. And then finally, we dot that with the feature edits of when we're comparing the protoform and the daughter reflex to get the weighted the weighted feature edit distance between G and Ch. So we call this directional weighted feature edit distance because our metric takes into account that the probability of some sound A changing to some sound B is not equal to the probability of some sound B changing to some sound A. So with regular feature edit distance, like the feature edit distance between sound A and sound B is equal to the feature edit distance between sound A and sound A. The feature edit distance between A and B is the same as the feature edit distance between B and A because it reflects it, but not with our directional weighted feature edit distance, which learns a different probability distribution of features changing for every protophone, right? And we train our neural network on a typological database of sound changes called index diachronica. Then, after we identify we score the possible intermediate sound changes with a transition matrix, we feed that transition matrix into a phylogenetic inference module, which uses a maximum parsimony method to basically try to identify intermediate propose intermediate sound changes that will minimize the cost of a tree. So their method in particular starts with a random tree and gradually tweaks the branches in the tree to find different new trees that will minimize the total cost of the tree. And the cost of the tree is simply the given by the cost that we define of the transition matrix. And again, the cost is just used to score the possible sound changes along each edge of that tree. Right. Finally, we evaluate with generalized quartet distance, which calculates the proportion of the proportion of quartets or groups of 4 languages in the gold tree that are arranged in the correct order. So this is very similar to recall an NLP task. And here's the gold tree. Sorry, it's a little blurry. And then here's the best predicted tree. And it might be very hard to tell because it's impossible for a human to calculate all possible quartets of the tree. But our best tree shows that our best predicted tree captures around 80% of the butterflies in the gold tree, where butterflies is just a variant of quartets. Okay, so we compare our phylogenetic inference module to 2 common baselines, a cognacy matrix, which simply records whether or not a daughter language has some cognate. So as I was saying earlier, there might be many ways to express the word I in a set of daughter languages. And we record whether or not a daughter language has that cognate or not, which basically is a baseline that only relies on lexical innovation. We also use a shared innovations matrix, which to record whether or not different daughter languages have different shared innovations or sound changes identified by a daughter. So this is much closer to what linguists use in practice when they're manually identifying shared innovations and when they're manually reconstructing the phylogeny. Okay. So our results show that our best tree can reproduce around 80% of the quartets of the gold tree. And we basically replaced the expert at different stages. So in stage 1, we replaced the expert's intermediate sound changes with those proposed by Panphone. Everything else is the same. And in stage 2, we replaced the expert's intermediate sound changes with those proposed by a phone graph. Now, not surprisingly, when we supervise the phylogenetic inference method with the experts provided reflexes, sound laws, the generalized quartet distance between the gold tree and the predicted tree is lower. And we find that when we try to learn sound laws using the minimal generalization learner from Wilson and Lee, the generalized quartet distance is actually quite high, which is unsurprising because we're not feeding in the gold sound correspondences / sound laws when we're trying to infer them ourselves automatically. So our work shows that much work remains to be done in inferring sound laws automatically. Now, let's talk about our submission or our eventual submission to EMNLP 2023. So basically, historical linguists, when they're performing protoform reconstruction and phylogenetic inference, they actually iteratively refine the tree and the protoforms instead of learning each one in isolation. We start off with a flat tree where we assume that all the daughter languages descend from the same proto-language, which is not accurate because there's actually intermediate internal nodes of the tree that we need to identify. Then we perform protoform reconstruction on the flat tree. So we can identify a series of sound changes along each edge of that tree and reconstruct the protoform. And then we can compare the proposed protoform reconstruction with each of the daughters to identify sound laws. For example, we can infer that S turned into sh for Romanian and E turned into A in this environment for Italian. Then, after we identify shared innovations, we feed that into our phylogenetic inference module, which identifies these internal nodes and groups different daughter languages together. And finally, after we do phylogenetic inference to get these internal nodes, we feed that back into protoform reconstruction, which should improve the protoform reconstruction because now we have actual internal nodes of the tree. And we can more accurately identify and group series of sound changes to get a better protoform reconstruction. And then with this improved protoform reconstruction, we can identify better shared innovations, which leads to a better tree, et cetera. So it's a cycle that leads until that we keep repeating until convergence. And that's what we're trying to replicate in joint reconstruction and phylogeny. So for those of you who've taken PGM, So we can talk about the generative story of sound change over time. So we can consider the language family tree as a directed graphical model, where the root of the tree is simply the proto-language. And along each edge, there's a series of possible sound changes. And then we can calculate the likelihood of that entire tree by taking the probability of the root multiplied by the probability of the sound changes on each edge. Great. And if you're curious about the generative story, so what happens is we sample a protoform from the root, and then we perform breadth first search on that tree, where for each child of the node, we can sample a series of sound changes from probability of the child given the parent, and we can decide whether or not to apply the sound changes to the parent to obtain a child. We repeat this for each level of the tree, starting from the root. Right. Now, of course, I've omitted the details of BFS for brevity, like checking the frontier, for example. Okay, so our goals in our EMLP submission is to capture the context of sound change, which previous methods did not really capture. We also want to conduct a fully unsupervised method. So there's recent work on neural unsupervised proto-language reconstruction, but unfortunately, the results are limited by the fact that they use a Latin protoform bigram language model. So just to reinterpret what that means, they're trying to predict Latin protoforms, and they claim their method is unsupervised, but they're sampling the protoforms or the Latin protoforms from a language model that's been trained on Latin protoforms. So we can't really say that their method is truly unsupervised. So instead, what we want to do is to train a phone-level multilingual language model over modern languages to reflect what a linguist would actually know. Like a linguist will not necessarily know all the languages in the world, but they will know different the probabilities of different phones across different language families. And that's what our multilingual phone-level language model is going to try to capture. We also want to insert linguistic priors. So we want to incorporate the typological prior from our sigmorphon work, as well as the phonological prior that captures the phonetic similarity between different phones. And we want to take that into account when we're proposing new sound changes. And finally, we want to be ambitious and work with hundreds of languages, 600 in the case of Oceanic. Now, He et al. 2022, the work I just mentioned, only works on 4-language subset of Romance currently. Right. So just to recap our sigmorphon submission and put that into context of joint phylogeny reconstruction, all we did in sigmorphon is to identify shared innovations, break down the sound changes in that shared innovation, and feed that into phylogenetic inference. But with our EMLP submission, we want to learn both the tree and the protoforms in a iterative fashion, but mutually reinforcing fashion. So again, we start off with a flat tree, step 1, and with that flat tree, we perform protoform reconstruction. And until we converge on a set of protoforms and a tree, we identify shared innovations, we perform phylogenetic inference on those shared innovations, and using that tree, we identify a more accurate reconstruction, and which in the next iteration of the loop is then used to identify more accurate shared innovations, which then get fed into phylogenetic inference, and etc. So the process repeats until convergence. And we note that our shared innovations algorithm that we talked about previously is deterministic because all it does is use the Needleman-Wunsch at a distance alignment algorithm. But for our both our phylogenetic inference and our reconstruction module, we're going to use Markov chain Monte Carlo inference because the posterior distribution in both cases is intractable. So we need to resort to approximate inference method like MCMC instead, where we sample from the probability distribution until it converges. Right. Now, finally, we want to note that historical linguistics don't have a gold standard when they're making a reconstruction because they're the ones making the gold standard. So moving forward, like we've talked about a few supervised methods, like a supervised reconstruction with an RNN, with a transformer, and with a VAE, but that's not necessarily realistic of the conditions a linguist has when they're doing reconstruction. So moving forward, we want to use unsupervised methods like MCMC to get a more accurate reconstruction. Right. Now, some other future exciting work that is currently being worked on by members of our lab, including Alex, who is here today. It includes using a generative adversarial network to learn a generative model of the proto-language. So this is unsupervised, and it's inspired by Bagouche 2021, who found that when probed, a generative adversarial network can output new words unseen in the training data that still respect the phonotactic constraints of the language. So that's pretty cool. And in addition to the GAN and the VAE directions mentioned earlier, we want to replace MC with variational inference and neural methods. So for example, there's a lot of work on neural phylogenetic inference in literature. We also want to improve our sound law induction method to be more robust across data languages. And finally, we also want to handle lexical borrowing or horizontal transfer into computational biology literature, which is going to be important because for Chinese and the Romance language families, there's a lot of dialect intermixing, and we need to account that because they pose a threat to the tree assumption that we made when we use the tree model of language change. Right. Now, finally, before I go into questions, I'll just talk about how you can join our research group. So I guess, I already mentioned this in the talks I gave at NLP and Conlang, but why should you join our group? Well, our group is working on applying state-of-the-art machine learning and NLP techniques such as variational autoencoders, transformers, and GANs to sound change. Right. Our project is also a great way to get started with research, and as well as a great way to learn about linguistics and different language families. Now, you'll notice that our NLP task uses more domain knowledge from linguistics than most NLP problems do. And finally, we can explore. Our group is exploring a relatively new field called computational historical linguistics, which means that given the it's easier to come up with more novel results than with a crowded traditional NLP problem. So here's a picture it's kind of blurry that I took, or that my mom took when we went to Korea last October, because when we were publishing our Wikihan Middle Chinese data set, I was able to attend a conference and fly to Korea for travel. So that could be you in the future if you publish your work.
I was on that speed one.
Oh, Bukchon Hanok or something
That's
like
a
that?
soul, right? That's a historic speed.
Yeah. Okay, now if you're curious about historical linguistics, I highly encourage you to register for Professor Christina Bjornhall's 80-287 language variation and change, which I took 2 years ago. Oh my God, I'm old. And then to join our, oh, sorry, wait, I'm so sorry. Sorry. Okay, so now to actually join our research group, we ask that you sign up for a 30-minute interview slot on the link right there. And if we find that you do not have sufficient experience for our project, we'll still see if we can refer you to other projects that the professors in our lab are involved in. Now, you'll hear back at the latest as to whether or not you can join a group by Monday the 15th. Yes, so take a picture of the QR code or use the bit.ly link to sign up for interviews. Yeah.